Hello. Question 5 for the midterm has two parts. The first part just asks us for a definition. So the first way I would think about defining W is a subspace of V, where V is a vector space and W is just some subset lying inside of there, would be by saying something along the lines of this. Oops, there we are. Really all you need is that W is a vector space when you think about it as inheriting its operations from the vector space V. You need it to be non-empty just to make sure that everything's okay, so you need that 0 is inside of that subspace. I don't have the answer key in front of me right now, but I think something like this should pass. Another way that I know was working was you could say that W is a subset that has these three properties. First of all, you have to have 0 inside there, or equivalently, you could also say that W is non-empty. Once you have that, then you only need that addition is well defined between any two vectors, and also that scalar multiplication makes sense. So I think something like this should work for definition 1, and this is fairly accurate as well. So the next part of the question asks us to work with this. It gives us this definition of a subset of the n by n matrices. You may not have seen this definition before, but we can still work with it in terms of the problem. The first thing that he asks us with this is to verify that it is, in fact, a subspace. So to do that, we just have to use those three properties to verify that it is. The second definition that I gave you, it's not actually a definition, it's sort of an equivalence according to our book, but I think that's okay. So first, let's go ahead and verify that 0 is in there. We can say 0 is inside of W, since 0 transpose, oh, I shouldn't be using the vector thing, sorry. Oh, well, it is a vector. Okay, since 0 transpose is equal to itself, which also is equal to minus 0. So we get that 0 transpose is equal to minus 0. So this verifies that it's in there. So now what we want to do is we want to verify addition. So now we can say if a vector v1 and a vector v2 are inside of our vector space W, then we want to verify that v1 plus v2 is also inside of W. And the way we do that is just by applying the transpose and hoping we get a minus out. So if we take v1 plus v2 and we apply the transpose, we know that the transpose is linear, breaks up over addition, so we get that this is v1 transpose plus v2 transpose. And by the definition of W having v1 be inside of W and v2 be inside W, we know that this is equal to minus v1. And this guy here is minus v2. So that's what transpose does to these guys. And we can then factor out this negative, and we get minus v1 plus v2. Okay, so that gives us that if we apply the transpose to the sum, then it pulls out this minus here. Okay, so that, by definition of W, gives us what we want. So now we have to verify this third part, and that just involves the scalar. So we can say that if V is inside of W, and we have some scalar, I'll call it A, I think I called it C before. Okay, then we want to make sure that A times V is inside of W, and this works because if we take A times V and we apply our friend the transpose, then what we get is that we can pull out scalars from the transpose. This is one of those things that we learned, I think it was at the end of chapter 2. And what we get is this. I'll maybe be specific with my parentheses. And now we know that we can apply the transpose to this guy and get a minus, so we get A times minus B. But now, because of the distributivity property of, or maybe this is associativity, property of multiplication of scalars in a vector space, we know that we can just pull out that scalar, that minus 1. Maybe we can do a brief little guy like this, right? Something like this, and this is going to be minus 1 times A V, and this is going to be, this is just going to be minus A times V. Okay. And so what we get is applying the transpose to A times V is going to be the same thing as applying a minus. So we get that thus W is a subspace of V. So that is it for this part of the question. We only have one more little part. This was part A. Let's go ahead and let's get to the next part. Here we are. Part B of this question asks us to just verify that this matrix, whenever I have some n by n matrix, this guy is skew symmetric. Okay. So how do we do that? Okay, it's pretty straightforward. All we have to do is verify that if we apply the transpose to this guy, then we get a minus. Okay. So if we say, let's go ahead and let A be inside of V, then A minus AT, if we apply the transpose to that guy, what are we going to get? Well, the transpose breaks up over addition, and this is kind of like addition. So we get A transpose minus A transpose transpose. We also know that transpose transpose leaves things alone, so we get A transpose minus A. Now if you look at this, this is a lot like what we started with, except it's kind of in reverse. So if we apply minus, it flips everything around, and it's going to give us A minus A transpose, which is exactly what we wanted. Okay. So we get that thus A minus A transpose is inside of W, our friend W, from before. Or we can say that it's skew symmetric. Thanks very much. If you have any questions, ask them in the comments below or in class.